Uncertainty. Why do we need to know this? This helps us be able to choose our glassware in our lab. So now we know each piece of glassware that we use, and actually everything you use in lab. Your balance has some error associated with it. Your glassware has error associated with it. What do we now do with that error that we know is associated with our measurements? We have to propagate it. I enjoy this word, I don't know why. Propagation, propagate, it just sounds fancy to me. So what we're doing here is rarely in lab do you just go in and I say, measure me 50 mils, and you measure 50 mils, and I say, good job, Sydney, lab is over. That was the whole lab.
Wait, can you do that?
No. So you measure things to make solutions, to then do a titration, to then do a thing. So you're like doing something with each of your measurements that you make. So depending on what math you're doing, you're either doing addition and subtraction, or you're doing multiplication and division. So there's different rules for how we're going to propagate addition and subtraction values versus multiplication and division. So in this example, we're just adding and subtracting three numbers together. I just did the math in the calculator. 12 plus 18 minus 10 is 20.28. But each of those numbers has error associated with it. So what is our final answer? What's the error in that final answer? So you can't just add those errors together. We do have to propagate it. So how do we determine the uncertainty after you do math? We combine, oh, that's exciting. That's a highlighter, sorry. We combine or propagate all error. So for addition and subtraction, our error, which our textbook calls like lowercase u, is what it does for error. So the error in the answer equals the square root of the error of all the values squared. So the error 1 squared plus the error 2 squared plus however many values you have, and then you take the square root of that. So let's look at the example above, or actually let me give you an example first. The next practice problem will be, so if we have 1 plus or minus 0.1 plus 2 plus or minus 0.2, the answer is 3 plus or minus what? So it's going to be 0.1 squared plus 0.2 squared, and take the square root of that. Shout it out when you get it.
0.22.
0.22. You must have good hearing.
I know.
That was pretty.
That was impressive.
0.22. We can only, now we have to, so this is where things get exciting. So now we're thinking about error, and now we are always thinking about significant figures. We can't forget about that. So we can only report 3.0 to that tens place, so we actually only care about that tens place. But even if we didn't know that, if we just look at our error, that it starts in that tens place, so we don't actually care about anything that comes after it. So we're really just going to report this as 3.0 plus or minus 0.2. And most likely there'd be a unit associated. So now, this is the absolute uncertainty. So when you plug into this equation, the answer it gives you is the absolute uncertainty. So now for this question up here, calculate what the absolute uncertainty is, and then looking back from your notes from yesterday, from there you can calculate your percent relative uncertainty. But step one is absolute. So what is your absolute uncertainty and percent relative? So it's asking two different things. absolute uncertainty is the equation we just used. So square all your errors and the square root.
Do we have to square these?
Yes.
Okay.
Yeah, that's the question above. Yeah, this is the value. This is called the magnitude of measurement. This is the error in that value. So that's the error. That's the error. That's the error. The more I say that word, the less of a word it sounds like. Error.
This
Is that what you're getting?
one like this, but like you, as long as you can't use this.
Well, we actually don't really care about anything after the 9 because we're saying that's the position where the error starts, and it happens to match up with your P6. So you would report 20.28 plus or minus 0.09. But write down that little 4 after it
Okay.
for your absolute error, because when you do your percent relative,
Now,
then it's just like carrying a number to help you. Perfect. And then percent relative is now error divided by magnitude of measurement times 100. So the error you just calculated divided by the value, your magnitude of measurement, times 100. So when we write our absolute uncertainty, we got 0.09 with more significant figures. The 09, that hundredths place is where we first start to see error, and that actually does align with as much as we know in this number, so you would report it 20.28 plus or minus 0.09. When you then calculate your percent relative uncertainty, it's worth carrying more significant figures. So I like to do that just to remind myself. I like write it like a small, like a subscript 4, even though it's not really a subscript. Or you can just leave it in your calculator, have your calculator hold all of those significant figures. And then our percent uncertainty is now our absolute error divided by our magnitude of measurement. What is that for this problem? That's that 20.28, and then it's asking for percent, so then we multiply it by 100, and what do we get?
Small number.
5 times 2 to -3%. I got,
Did you multiply by 100?
I got 0.46%.
Second.
That's what, oh, okay. 0.
That calculation. Oh,
So 09, did you maybe drop some sig figs? Or maybe you did all the sig figs? Double check that. 0.46%. This, now that we're in a percent, the sig fig rules do not apply. So I like to usually just do 2 when you're talking about a percent. So 0.46. So then you would report this number, 0.28 plus or minus 0.46%. Super important to write the percent, because that's the only thing that's differentiating this error as being relative, the percent relative, versus this is our absolute error. So if you do that, make sure to put your percent after it. Questions on now our absolute? Because now we're going to up the ante And now we're going to talk about when we are doing multiplication or subtraction. So in addition, multiplication or division. So now when we propagate is this thing here when we're under the square root, when we're squaring and under the square root, that's the propagation. So now when we're propagating for multiplication and division, we're actually propagating as relative uncertainty. So our answer, error in our answer is divided by our measurement. So that's now relative uncertainty. It's relative to the measurement. This equals our measurement of A divided by measurement A squared, measurement of B divided by, error in B divided by measurement B squared, so on. So your answer is in relative uncertainty. And if you want to get out of your relative uncertainty, you multiply it by your measurement. So if you multiply that side by your measurement, you're now in your absolute uncertainty. So that's how those two are related. So now let's put some numbers to this. So we have something times something divided by something. I already did the math for the measurement. Now you need to propagate our error. So remember, it's going to be 0.08 divided by 32.81 squared.
So even for division, do you add it as well?
Yeah, because we have to add the error. That was a good question. Kim just asked, even though it's a division and multiplication problem, we're still adding the error. This is us adding the error for each measurement that we took. So we have to combine the error. So you're always adding when you're underneath the square root. What did you get?
For the relative?
Yeah, for the, relative.
4.7 times 10 to the negative 3.
Yes. And I'm gonna write it this way just because that helps me check my sig figs, like our matching. 0.0047 is our relative uncertainty. And now, how would we get to our absolute uncertainty?
Multiplied by the 93.60.
Yep, and what do we get for that?
0.439.
Okay.
Which you multiply by 100 or no?
So if we wanted to get our relative into percent, which is what it asks for, we do need to multiply that by 100. So the way we would report that would then be, oops, go away, Vladimir, 93.62 plus or minus 0.47%. That would be our percent relative, which is what the question asks for. And then if we wanted to report it as absolute, let's think about these sig figs up here. Where do we start seeing our error? Well, we start to see it just like right at the 0.4. So that's our 10th place. So there's already error in this 0.6. There's already error there. So we actually don't care about anything after it. So we would write this 93.6 plus or minus 0.4. So pause and think about that. Does that make sense?
Wasn't the absolute error 0.0047?
That is our relative.
Okay.
So when we plug it into this equation here, when it is the error over our measurement, that's spitting it out to us in relative uncertainty. So 0.0047 is our relative. This question just happened to ask for percent relative. So then we just have to multiply that by 100 or move the decimal over twice to get into percent. And then always put that percent sign there so we know. Then it asks for absolute, and the way we do that is our relative uncertainty equals our absolute error divided by the measurement. So then if we just multiply that 0.0047 by our measurement, that's then when we got this 0.439. I mean, it's complicated. Or it's like secular, error is secular. So that's why we're gonna practice it. That will be like on your homework. So the main thing here is absolute and relative uncertainty are two different things. Absolute is just that plus or minus a number. The relative is when it then compares it to the measurement. So it's relative to the measurement. I am probably always going to ask for it in percent because that's how I like to be able to differentiate what this plus or minus number is. If there's a little percent sign after it, I know we're just talking about percent relative. Then on top of that, the way we propagate is differently. So if it's addition or subtraction, we propagate just by taking our absolute errors and squaring them, and then taking the square root. Versus if it's multiplication and division, we propagate the relative error. When we are in lab, almost all of your propagation is going to be multiplication and division. Because just think about all the dimensional analysis you set up. If you're converting grams to moles, or if you're doing a dilution, M1V1, that's always multiplication and division. So this is the one we'll use most.
Why did you round up the 93.62 to 93.6?
So my answer is, the question was, why did I round up? So I didn't know to round up until I calculated my error, which is 0.439. I actually don't care about all of those sig figs because this is already telling me there's uncertainty in this 10th position, that 0.4. So there's no reason to report my measurement past that 10th place because I already have uncertainty in that 10th place. So I just report to my 10th place, 93.6 plus or minus 0.4. Because everything after that, we already know that there's error. There's no reason to suggest we know to more certainty than that 10th place. Okay, questions? Okay, so those were just numbers. Now we're actually going to add our chemistry to this. So this is a type of problem where we care about the uncertainty. So we have a 0.001 molar solution, and we made it from a 1 molar stock solution. So in our head, this is a dilution. So we calculated calculate the overall uncertainty for a two-step dilution, and then it just gives me lots of numbers, and already I'm like, I don't even know what she's asking. Okay, so let's break this down. Calculate the overall uncertainty. So is that absolute or relative?
Absolute.
Absolute. So we're trying to get into our absolute uncertainty for a two-step solution using, and then I'm giving you glassware that I'm using. So here, this word dilute or a solution was prepared. Both of those tells me that we just used our M1V1 equals M2V2 equation. So a dilution just means we did multiplication and division. That's helpful to me because that means I need to use the propagation of error for multiplication and division. So because we're just adding all the errors, I actually don't care what's being multiplied or divided by each other. I just care about what the error is in each of those things. And the question didn't actually give me any error. It just said I used a 20 ml pipette. So that's when we have to go back. Oh, sorry. Go back to chapter 2, to this table. And it says I used a 20 ml pipette. So that's where my error is coming from. So you're gonna have to refer to this table. And before you flip back, stay on that page, the table page, let me add some more larger glassware for volumetric glass. For 250, 250, 500, and 1000, the volumetric glass is 2, 4, and 6 mils. So when you use a 1,000 milliliter volumetric flask or a 1 liter volumetric flask, there's actually error plus or minus 6 milliliters. So if you're using it correctly and you're buying the Class A volumetric flask and you're a perfect person working at 95 degrees Celsius at a 1 atmosphere condition, you still might be 994 to 1,006 milliliters if you're perfect. And we all know that we're not exactly all perfect, but that's the error that you'd still be getting. So, going back to our chapter 4. So what you need to do for this question is you just need to set up your propagation. So your answer divided by your measurement. What is your magnitude of measurement here? What's the value that we're calculating the error in?
0.001 molar.
Yeah, beautiful. 0.001 molar equals square root. And we used a 20 mil pipette, a 1,000 mil volumetric flask, a 25 mil pipette, and a 500 mil volumetric flask. So that means 4 pieces of glassware, 4 errors. Do you want me to write the first one, or you guys are on the same train I'm on? Okay, let's write the first one. So I'm just going to start at the beginning. 20 mil pipette. I look at my table. My 20 mil pipette is 0.03 error in 20 mils squared. So that's the error in that first piece of glassware. Plus, and now look up your 1,000 mil flask. when you just plugged that in, what did you get for your relative uncertainty? So when you just did the square root of those numbers.
0.0117 or 0.0.
That's fine, we can carry sig figs here.
Okay.
So second or different? That was the second with a question mark behind it.
It's a lot of numbers.
0.0117, is that what everyone got?
I just got point oh one.
Yeah.
I was like, it was close enough that I was like, okay, you know. Like,
So,
no, it's,
there are no numbers that are close enough anymore. That is quite different. So I'm assuming that somebody used their calculator as their brain to hold all the sig figs, and maybe somebody was like transcribing each of those together.
I used the calculator.
Oh, you did use
I
calculator
could have made, let me do it again.
because I also got this other one, 0.0101,
Yeah, okay, I messed it up.
and that's why we do this, because calculators just try to trick us. So we got 0101. So that is relative. So now the question's asking for my overall. So I have to multiply that by our 0.001. And what do we get there? And this just seems funny, but remember, so our number is 0010 molar. So plus or minus, it should be how many zeros? What did you? 0.001 is what? Is that 4 zeros?
Hmm?
1, 2, 4. Yes or no? Second or different? Okay.
Why did you put why did you put times 0.001?
That's
Oh,
this
sorry,
one over here.
okay.
I tried to do it a different color.
That makes sense.
So that's us that's our measurement. So that's us getting out of relative to our absolute. And then how we would then report that number is 0.0010 plus or minus, this is our error. So we're already saying there's error in this, I don't even know what place this is, if it's behind the decimal place, billionth, billionth,
lots of
billionth.
lots of
Whatever this position is where we start to see our error. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. So we actually can add a 0 in terms of our, so we don't need these. Molar. And this is just the silliest way to write this. So I would probably want this written as 1.0 plus or minus 0.01 millimolar. And then that way you're not like counting your zeros.
What if you did like 10 to the negative 5 molar? Is that like equal?
But that's your error is 10 to the negative 5. So your measurement's only 10 to the negative 3. So if your measurement's 10 to the negative 3 and 10 to the negative 5, I'm already
both
confused.
sides. Sorry,
so no.
sorry.
So I would
Yeah.
write, choose one unit and go with it. So we care about this in analytical chemistry because in Gen Chem, I mean, Dr. Monceau doesn't even use flasks or measurements. He just dumps. So he does not care about significant figures. But in analytical, we are teaching you to now have a high level of accuracy and precision in your measurements. So we actually do care about that plus and minus 6 mils when you're using a volumetric flask. So I would put a little star next to this problem because when we are in lab, there might be questions that ask you to calculate the error in that solution. And what I mean is when you use this piece of glassware and this piece of glassware to make your solution, what is now the error in that solution? And this, we did like a 2-step dilution here, so it might actually be more simple than this. If it was just a 1-step dilution, you basically don't have those second 2 numbers. But this is something that you'll be seeing. That was fun. This is where we start to get a little in the calculation of error. Because imagine when you actually go into lab, I mean, you are making a solution and doing a dilution and then using a burette and then doing an M1V one. So I mean, you are doing like a lot of propagation of error. So, moving on now to, we go into lab and we said that if we have a high number of measurements, we get something that is Gaussian in distribution. Now we're going to do a little bit of like a stats class. So I mean, there's like lectures of this and I'm making it a 10-minute part of our lecture. So if we have our mean value, and you are going to see, so math statisticians, biologist statisticians, and we just tag on chemist statisticians, we all use different letters to mean the same thing. So it's going to get hopefully a little confusing. But this is now using mu as our mean. Previously we used mean as x bar. This came out of the same textbook. People are just hilarious. They're like, things aren't confusing enough. Let us just change our notation. So now we're saying our mean is x bar. There actually is a difference here. X bar is our experimental mean. Mu is like our true mean, but for us, we're gonna say that's the same. So when we now start saying plus or minus a number, what do we mean? So if we are within one standard deviation, which now we are calling sigma, sigma is our little s, one standard deviation is our little s for standard deviation. If we are in one standard deviation of our true value of our mean, so we do mean plus or minus, so it's in the positive and the negative direction, we're actually accounting for this much of our curve. So from this figure, there is an X% chance of the population's member, the number falling between that plus and minus 1 sigma. So what percent chance would that be?
68.246.
Yeah, 68.26. So 34.13 plus 34.13. So our 68.26%. Now, that's kind of a high percent, but also kind of a low percent. Like if you only had 68% chance of living, you'd be like, are there better odds that I can take, right? But like, most likely the number's under there. So in order to get an even higher percent chance of the true value falling within that range, we can go to 2 sigma. So now we're adding this teal section. So plus and minus 2 sigma, what percent chance do we have falling within that range?
Like
95.44.
95.44. So I would take that better, right? A chance to live, 95% chance. Okay, we're looking good. Now, what if we went to 3 standard deviations or 3 sigma plus or minus? What's our percent of falling in there?
99 point, I don't know, 6, 8.
72, 99.72. So almost 100%. So there's still an itty bit of the population that's outside of our 3 sigma range. So why this is important is this tells you your confidence interval. How sure are you that the true number falls within the range that you're giving? So your confidence interval is a range of values where the true value falls within a specified probability. So if I said a 95% confidence interval, so that would be this 2 sigma, that means I'm 95% confident that the true value falls within whatever that x plus or minus 2 sigma range is. And we give this an equation, so confidence interval, big CI, equals the mean plus or minus TS over the square root of n. T is your confidence level value. And this comes from a table. You don't know this unless you have a table. Little s is your standard deviation, and n is your number of measurements. So there's tables like in the back of analytical textbooks, in the back of stat textbooks that are for like all of these different percentages, confidence values for a whole range of n's. We are typically concerned with the 95% confidence level. Basically, it takes more time and money to get to the 99. So we say, okay, 95 is a lot better than 68, so we're gonna go with that 95% confidence. So this is the table we're going to use in this class. This is values of t for the 95% confidence interval. And it's degrees of freedom listed 1 through 100 all the way to infinite. A degree of freedom is n minus 1. So if you have 5 measurements, your degree of freedom is 5 minus 1 or 4. So degrees of freedom is minus 1. This is your t value that you plug into the equation. So let us see this in action. If you took the math of 10 pennies and you calculated the mean and standard deviation, which I gave you here, calculate the 95% confidence interval. So we know to use that confidence interval equation because it told us to calculate the confidence interval. The 95% comes from that t value. So if it said calculate the 90th percent confidence interval, you would still use that equation, but then you would have to find a table for 90% confidence interval. So it equals the mean, which I gave you, plus or minus t times s. So what is our t if we took the mass of 10 pennies?
2.262.
Perfect. Times the standard deviation, which I gave you in the problem, divided by the square root of n, which you took is 10 measurements. So what did you get for that?
Like the whole thing.
That plus or minus number, yeah. 2.96 times 10 to the negative 2, so 0.0296, right? 296. And we have to think about our sig figs here. So if we're already losing confidence there, we report this as 3.28 plus or minus 0.03 grams. Did everyone get that value? Okay. Now we are going to pause because this looks an awful lot like mean plus or minus standard deviation, right? So we can report our mean as 3.283 plus or minus our standard deviation of 0.042 grams. Or we can say that our 95% confidence interval is 0.03. So pause and think about what is the difference between standard deviation and confidence interval. And chat with the person next to you and see, like if you had to put it into words, if you had to explain to grandma what the difference between a standard deviation and what the difference between a 95% confidence interval.
Standard deviation, the t-value? Is that what we're looking at?
She's asking what the difference is between standard deviation and what
Could you tell
the
grandma?
99% confidence interval is.
I'd tell Lucas.
The T
Come up
level?
with something.
Well, I can't tell my grandma, I can tell Lucas is smarter than me.
We'll use a high frame.
My grandma doesn't know what
You
she
guys
is.
can come up
I can make
together.
something up for my grandma.
What number?
Make something up for Lucas.
Lucas had pretty good answers.
Oh, for the degrees of freedom or the t-value?
No, for like the 99% confidence interval, which is
Like someone, all your court
that 0.03 versus the 0.042, which is standard deviation. Like, what's the difference between the two of those values?
One's coming from the experimental mean and one's coming from the true mean, is that it?
So yeah, standard deviation is coming from experimental. So if I report a number with a standard deviation, that just means that after my 10 measurements, when I do my standard deviation, that number, and if we look at our definition for standard deviation, we say is how closely the data is clustered about the mean. So that just tells me how far from the mean all of my measurements are. So that tells me about my accuracy or precision.
Precision.
Precision, how far or close to the mean I am. So it's like a bigger standard deviation means you are less precise than a smaller standard deviation. Now my confidence interval tells me accuracy, a range of values that falls within a specific probability. So I am 95% sure that the true value falls like within this range. So now confidence interval is talking about our accuracy. How accurate are we? How sure are we that the true value is, like your experimental value is near your true value? Okay, we'll end there. So before, when we come in on Wednesday, we are actually going to be looking at a homework question together that goes over confidence intervals, and then we'll pick back up on our notes.
Is the homework 2, is that still due on Friday?
Homework 2 will still be due on Friday, so you can start working on it for chapter 4.
Okay.
Yeah, you have. It doesn't matter what class, someone in that class.
I need to get these notes over to